Welcome to lecture number 14. So today we are going to learn few fundamental aspects of statistics. Okay. So here we are only interested about some statistical aspects that are relevant to quantum mechanics. So let's see. Suppose we have a function psi, which is an eigenfunction of the operator b. All right. So if it is the case, then definitely we can write this equation something like this. Okay. So that means that this is my eigenvalue bk. So why did I write the subscript k? Because psi can have different values 1, 2, 3, 4 depending on the number of modes. But let just assume that I am not writing n and bk is some eigenvalue. So in this case, so this operator, okay, so the operator actually represents some physically measurable quantity. Okay, so some property, some physical property. So it represents some physical property. Okay, so therefore for an example we can take that we have the energy operator H, Hamiltonian operator. So this represents the physical property energy, means operator of energy. So if it works on psi n, so definitely we get En psi n. All right, so here En represents bk. So this is the energy. So we can predict. So this energy is predictive from the equation. Which equation? An eigenvalue equation. And not only that, if we are going to measure by some experiment the energy of the system, we will always end up with one value, that is En. All right. So this is an advantage of having an eigenvalue or an eigenfunction or an eigenvalue equation. Okay. So now let's think about the other end. So the other end is, let psi be not an eigenfunction of the operator b. All right. So we cannot write in this case that b psi is equal to some constant multiplied by psi. No, we cannot write that definitely, because in this case psi is not an eigenfunction of b. Okay. So the thing is, so this b operator represents a physical property b. Okay. Now the physical property b is measurable, means we can actually try to measure by some experiment. For example, we can think about, this could be momentum. So momentum is a physically observable quantity, so we can try to measure a momentum. So the corresponding operator is momentum operator. Now if the momentum operator operates on a already existing wave function psi, it is not giving me the exact eigenvalue. That means it is not fulfilling the eigenvalue equation. So then what happens? Then definitely we can try to measure b. Okay, all right. So every time if we try to measure b experimentally, we get some values. Okay, so we get some values, and those values are called observables. All right. Now the thing is, depending on the experiment, we may have different experimental conditions. So every time we try to measure the observable, out of an experiment, we may get different observables, okay, or we can get a number of possible values, okay. So neither of the values is wrong, okay. So we get many possible values because we do not have an eigenvalue equation. So what we do in that case, so we consider the average of all the possible observables and we call it an average value. All right, so let's write that thing freshly so that you can understand. So whatever I told you just now, so I had a summary written on the board. You see, we consider an average value of the observables, okay, which is nothing but a number of possible values, and those values cannot be predicted. So let's write these values can't be predicted previously by any equation because we don't have an eigenvalue equation of the property B for a system whose state is psi, okay, so which is already solved and its state is psi, means the solution as a wave function is psi, but definitely not an eigenfunction of the operator B. All right, and in quantum mechanics every time such systems appear, so we will come to that a few minutes later into the lecture. So mathematically we consider the average value of all the possible outcomes and is denoted as this triangular bracket B is equal to average of all the possible outcomes weighted by their likelihood. So this phrase signifies nothing but the weighted average. Okay, so we consider the weighted average of all the likelihoods. That means any event, any outcome, how many times it appears, means if it appears once versus if it appears 100 times, they have some significance into the total outcome or the average outcome. So now we will try to mathematically represent this average value B. So let's take a look. So the question is mathematically how we count the average. So if we talk about simple arithmetic mean, so suppose in a class of 10 people we have different ages of different people, like 6 years, 7 years, 8 years, 7 years, etc. Then we simply add them up and divide by the numbers, we get the simple arithmetic mean. So that's how we represent it in this formula. It is sigma of bj divided by n, the total number, okay. But in this case this is slightly different, so this is called the weighted average. So this average value is taken by multiplying each possible value with the number of times it appears, okay. So this is the possible value B and how many times this B appears, so divided by the total number of appearances. So this is how we calculate the average value. So this can be further written simply as NB divided by N, all right, so whole B and multiplied by B, all right. So this factor over here, the summation of NB over N, it can be further replaced by this terminology PB. We can only write if, okay, N is a very large number, okay. So this may not be appropriate if the number of this N value is a small number, but if N is very large number, large means 10 to the power 10, 10 to the power 20, etc., very large number, then we can express this quantity, so the number of times it appears over the total number of values, it can be replaced by the term probability. So here PB stands for the probability, means the probability of appearance of the value B. Okay, so it represents that how many times a particular value is expected to appear. Okay, so this is what it is. So now we can write this B as this. So only one condition, that n should be very high. In fact, this above equation we can write it in a general manner, in a simplified manner. So that means it is not only we can write this equation only for any operator or observable property, we can write in a general manner for any quantity, say x. So x is any observable. All right, so for any observable, this thing can be written something like this. So xj function fxj, j is equal to 1 to n. Okay, so this means we can write that fxj, xj is the particular value. All right, and fxj, it is the probability of appearance of the particular value xj. So we can write it is the probability, or in other words the probability function, for realization of a particular xj. All right, so that's what it appears. So fxj is the probability of the realization of a particular value xj. So we would make ourselves familiar with this formula of average value. Okay, so now the question is, what do we do with this kind of expression? All right, so in order to know more detail about it, we have to know two more quantities in terms of statistics. Okay, so we have already known the average value, expression of average value, and two more things. Okay, so let's erase this board and let's quickly define what are those two. So few other important statistical terms that we need to learn is called, one of them is called the second moment. If you have a preliminary statistics book, textbook, then you can actually find this. So this second moment is defined as this. So it is the average of x squared. So similarly, it is defined as this, x square xj square fxj. All right, so this is analogous to, this formula is analogous to the moment of inertia. Okay, so you can remember the moment, the formula for moment of inertia, and somehow this is analogous. Now another very important term is called the second central moment. Okay, so this second central moment is denoted as sigma x square. All right, and this is defined as something like this. So this is the average of x square minus average of x square, and it can be shown that this is greater than is equal to 0. All right, and this is called the second central moment, or it has another name. So just a moment. Okay, so this second central moment is alternatively known as the variance. Okay, and remember the variance is square of sigma x. So in other words, what is sigma x? The sigma x is nothing other than the term you might have learned earlier or heard of. It is called the standard deviation. All right, so now you will get an idea that why we are actually talking about this sigma x, because this standard deviation of x in x is nothing but, it is, we can express as the uncertainty of measuring the physically observable property x. Okay, so the uncertainty of x can be represented by sigma x, where the sigma x square is represented by this formula. All right, so with this thing, statistically we have a better understanding of uncertainty of a physically observable property. So very simple. So if you want to measure something experimentally, we have various possible values. Okay, so that means we have some uncertainty of measuring that. So how we can express those statistical things, then this formula would definitely help us. So for the rest of the lecture, we will apply how we can utilize this formula sigma x square, the formula of variance, to see what is the uncertainty of momentum and uncertainty of position of a free particle in a one-dimensional box. But before we go further, let me just quickly give you an example of this eigenvalue and expect an average value. So suppose there is a class of 10 people and some examination has been conducted, and if everyone of the students got the same number, say everyone got 66 out of 100, okay, so their average is 66 while every individual's marks is 66. So we can say, as if we can correlate that the entire class is in an eigenstate. Okay, so here when we call h psi is equal to e psi, so when the eigenvalue e comes out, it is also the average value. So here the average value is equal to the eigenvalue, similar to the situation in class. But in other way, if 10 different people secures different marks, then what we do, generally we take an average of all the marks they secured. All right, so and once we do the average, definitely there comes another question, the standard deviation. Okay, so I hope I was able to express a little bit similarity between the situations that we can readily recognize versus the quantum mechanical situation. So in quantum mechanical situation, these are somewhat crudely comparable, but not exactly. Anyway, so let's apply our concept further in a free particle in a one-dimensional box, and then our understanding would be clear. But before that, we must remember such formula. Okay, so let's erase the board and carry on. So now we will try to see how those statistically defined quantities can be expressed in terms of quantum mechanical language. So for example, now we know that the average value of x, okay, this can be expressed as something like this, xj f xj, j is equal to 1 to n. All right, so we have already seen this formula. So now the question is, how can we express this in quantum mechanics? So fxj, so this is the probability function, all right, or in other words, this is actually the probability. So the question is, how can we define the probability in quantum mechanics? So in quantum mechanics, this probability basically is represented by the square of the absolute value of psi, all right, psi square, or in other words, this is nothing but psi star psi. okay, provided psi is imaginary. So if that is the case, then probably here we can replace this part by psi star psi. So therefore, so this is the summation. So summation of xj. So therefore, in quantum mechanics, instead of summation, we can use the integration. So for the same thing, we can write integration of, so that xj can come inside. So we can simply write x, because now we are integrating it in a continuous fashion. And then instead of fxj, we can definitely write psi star psi. Of course, we have the integrating with respect to x, means we have the integrating element dx. All right. So now this becomes our average value x. Okay, good. So now my question is, so x here, the way we have written, so the question is the x that appears here, is it multiplying on psi star psi, or is it actually operating on psi star psi? Okay, so you understand. So whether x is an multiplication factor, or what if instead of x, if we have an operator like ddx. Okay, so why I'm asking this question, because suppose if we want to find the average value of px. Okay, so the average value px means for the observable px we should have an operator. So it comes from the operator px cap, which is the momentum operator, and the value of the momentum operator is this, right? Minus ih cross del x, or minus ih cross ddx. All right. So the thing is, so therefore, if I want to find out the value of average value of px, so what should I write here? So definitely we have the psi star psi dx, but then what should we do? So can we write directly px, or can we write this value over here? So if we write over here, then definitely this would not be the same multiplication factor like x. Okay, because then this would operate on psi star. So the question is whether x is operating on psi star psi, or x is acting on a multiplication basis. Depends on the operator. So if x is a position operator, then it would act it would act in a multiplicative manner. But what if it is not, it does not act as a multiplicative sense? So in that case, we should have a definite, clear-cut definition of px or x when the corresponding values or corresponding observable can be represented by a operator. Okay, so in order to find a better definition, so let's clear the board and try to find. So here we go. So let's remember once again the example I told you, that uh, for an equation, right? So where we have h psi n x is equal to e psi n x, okay, or e n psi n x. So h is an operator for energy, and we all know that h stands for minus h cross square 2m ddx square plus ux. So the kinetic energy operator plus the potential energy operator. All right. So if we try to measure energy of a system which is in state psi, we get the value E predictively. So here the eigenvalue is equal to the average value. All right. So here we can write the eigenvalue is equal to the average value, because the system is in eigenstate with respect to the energy operator H. Okay. So if that is the case, so we take this equation and let's do something. So what we do here is this. So we both multiply by psi nx in LHS and RHS. So or we write, let's do this simple exercise. Psi nx star means we multiply it with its complex conjugate. All right. So why we are doing it, it would be clear to us later. Psi nx en psi nx. All right. So from this we can definitely write this, and then what we can do is now we can integrate both LHS and RHS, or what we do is we integrate, and if we integrate, definitely we need the integration factor dx. Okay, all right, and we have our appropriate limits. Okay, so I'm not writing it, we have the appropriate boundary. So what we get on the RHS, now let's assume that the psi nx is already normalized. Okay, now en is a constant eigenvalue, it is not an operator, so constant, and it is acting on a multiplicative manner. So we can take en out of this, so we can write en, and then we write psi star nx psi nx dx. Now if we assume that psi nx is normalized and within the appropriate limit, this value becomes 1, because this becomes the total probability of finding the particle within the said limit. So this becomes en. All right. Now we have already assumed that the eigenvalue is the average value. So we can also write this en is nothing but the average energy. All right, for that particular value of n. Okay. So in general, we can write that this can be the average energy of the system. So what relationship we got here? We got that the average value of energy is the operator for energy, and it is sandwiched by these two wave function. One is its complex conjugate and another is the function itself, dx multiplied by dx, and its whole under the integration within the appropriate limit. All right. So if this is a true expression, then for any average value, all right, any average value of any observable, say C, okay, so C is the corresponding observed value of the operator C. Okay, so here E is the concerned observable of the operator, energy operator, which is H cap. So for C cap we have C average value, so we can definitely express this as psi star C cap psi dx within the appropriate boundary. So this may be our new definition or the standard general definition of any average value. And this approach, you see, because C cap, this operator, is sandwiched between the two psi's, so we call this is a sandwiched approach. Okay, so we call this a sandwiched approach. So therefore now we have redefined the definition, quantum mechanical definition of average value. So what is this? So once again we write this. So we clear the blackboard, clear the whiteboard, and we write this. So the average becomes, say we have an operator A, okay, and the corresponding physical observable is A, and the average value of A, definitely we can write psi star A cap psi dx within the appropriate limit. So this means this operator A is operating on psi first, gives a value, and that value is being multiplied with psi star, and whatever the value with respect to dx, we have to integrate within the appropriate limit. All right. So with this, let's take an example. So let's take an example that how we can find x. So where x is the average position and the corresponding operator is the position operator x cap. So my question is, what is the average position of the particle? So the question is, for a free particle in 1D box. Okay, so this is the question. So how we can answer that? So definitely from this definition we can write that x is, so for a free particle in 1D box, so psi star x. Okay, so x is the operator psi dx. Okay, or in fact we can write it in bit more elaborate manner. So psi star x, x cap, psi x dx, and we know the limit 0 to a because we have defined in such manner that it is limited within the boundary 0 to a. So this should be the average position. So what should be the average position? Because now we can write psi star x. So now, or psi x, whatever. So the value of psi x is b sine or root over 2 by a sine n pi x by a. So therefore, so here we can write, if you remember, psi x, the normalized wave function is root over 2 by a sine n pi x by a. So root over 2 by a, those are constant, they can come out. So 2 divided by a, 0 to a. All right. So this x operator becomes a multiplicative operator. So this is x. So everything under this integral are acting as multiplication. So this x comes out. So this x comes out here, and then rest of the things here becomes sine square n pi x by a. All right. So therefore we have a new expression for our dx, definitely. So we have a new expression for this, that is the average of x, that, or in other words, the average position x is equal to 2 over a multiplied by this whole integral. The question is, can you solve it? All right, so if you solve it, we will try to find the average position x. So now, before we finish today, the question is, can you expect the average position in a particle in a box? So here we have the particle in a box, right? Here we have the particle in a box. So 0, a, and particle is ready to move anywhere between 0 to a. So as an average, where do you expect the particle to be, its average position? Okay, so at the side? No. So on an average, because since a particle has an equal probability to go anywhere between here and there, so on an average, we expect it that the particle to stay at the middle. So the position is x is equal to a by 2 if this position is defined by x and the length is a, exactly at the midpoint, a by 2. So now your job is to show that this entire integral, okay, comes out to be a by 2. So mathematically, if you can prove this, then I'm sure you have learned one very important value, that is the average position of a free particle in a one-dimensional box. So similarly, once we know x, we can predict px. All right, that is the average value. So what that we have to predict? So why we are doing this? Because I want to measure the uncertainty of position sigma x for a free particle in a 1D box, okay, and I also want to know the uncertainty of momentum for a free particle in one-dimensional box sigma px. So how do we measure? Because we already got the definition. Sigma x is this, right? If you remember. And sigma px is definitely this, if you remember. So out of these definitions, we already have the value of x. So this one, we already have this. And we know this is a by 2. And if we square it up, definitely it would be a squared by 4. So we have to get this value, we have to get this value, and we have to get this value. Then only our complete uncertainty of measuring x, that is sigma x, and so this should be sigma x square or sigma px square. Okay, so pardon me for the mistake. So once we know that, we know the sigma square x and sigma px square, which is the variance. So once we know the variance, we take the square root of it to get the standard deviation, which is the uncertainty of sigma x and sigma px. And then probably we will try to understand the underlying principle of Heisenberg's uncertainty principle. All right. So I hope you have understood a major part of statistical significance of some of the quantum mechanical aspects. So please try to follow the textbook, and in next lecture, that is lecture 15, we will try to solve all these and uh, try to get a deeper insight of Heisenberg's uncertainty principle. So till then, see you in the next lecture. Goodbye.